Welcome, my friends. One common way to solve a system of linear equations is through substitution. Here's an example of a system of linear equations. The method of substitution should be used when one of the variables, either x or y, can easily be solved for. Conveniently, we notice that the second equation in this system is already solved for x, indicating that substitution might be a good method to use to solve this system. The way substitution works is, one of the equations is substituted into the other equation. In this case, the second equation tells us x is equal to 3y plus 18. The first equation also has an x term, so we can substitute the expression for x from the second equation into x for the first equation. This leaves us with 5 times 3y plus 18, which was x, minus 3y, is equal to 30. All I've done is written the expression 3y plus 18 in place of x. Notice the resulting equation only has y terms and no x terms. This allows us to solve for y. The first step will be to distribute the 5 to 3y and 18. That leaves us with 15y plus 90 minus 3y is equal to 30. Combining our y terms by taking 15y and subtracting 3y, we have 12y plus 90 is equal to 30. Subtracting 90 from both sides, we have 12y is equal to negative 60. Dividing each side by 12, we have y is equal to negative 60 over 12, which simplifies to negative 5. Now you can plug in your value for y into either of the two original equations to solve for x. The second equation looks a little bit easier, so I'm going to use that one. We have x is equal to 3 times negative 5, our y value, plus 18. This simplifies to x is equal to negative 15 plus 18. Negative 15 plus 18 is equal to positive 3, so that means x is equal to positive 3. Altogether, our final answer is that x is equal to 3 and y is equal to negative 5. We could plug these values back into each equation to make sure they are correct. In the first equation, we have 5 times 3 minus 3 times negative 5 is equal to 30. This simplifies to 15 plus 15 is equal to 30, or 30 is equal to 30, which is a true statement. In the second equation, we have 3 is equal to 3 times negative 5 plus 18. This simplifies to 3 is equal to negative 15 plus 18, which again simplifies to 3 is equal to 3, another true statement. This verifies that our solution of x equals 3 and y equals negative 5 is indeed a solution to this system of linear equations. Let's try another example. We don't have x or y solved for in our given system, but we notice that we do have a y term without a coefficient in the first equation. If we add 2x to both sides, we will have solved for one of our variables, leaving us with y is equal to 2x minus 8 in our first equation. Now we can substitute our expression for y of 2x minus 8 from the first equation in for y in the second equation. The result is 5x minus 4 times 2x minus 8 is equal to 23. Now we have an equation in terms of only x, and can therefore solve for x. First, we distribute the negative 4 to both 2x and negative 8. We get 5x minus 8x plus 32 is equal to 23. Combining our x terms, we have negative 3x plus 32 is equal to 23. Subtracting 32 from both sides, we get negative 3x is equal to negative 9. Dividing each side by negative 3, we get x is equal to 3. Now we can plug x equals 3 into either equation. The first equation looks a little bit nicer here, so I'm going to plug into that one. We have negative 2 times 3 plus y is equal to negative 8. This simplifies to negative 6 plus y is equal to negative 8. Adding 6 to both sides leaves us with y is equal to negative 2. That means our solution is x is equal to 3 and y is equal to negative 2. There is another method of solving a system of linear equations called elimination, which tends to be a bit easier than substitution if it works out. Elimination uses the idea that adding two equations together is a valid manipulation of our system and can sometimes simplify the problem. Specifically, what you want to look for is if the coefficients on the same variable have the same value and opposite signs in your system. For example, consider this system. If we wanted to use substitution, we would have to do quite a bit of work isolating either x or y in one of the equations before substituting. Elimination is going to be a much better option here. Notice the coefficient of y is 2 in the first system and negative 2 in the second system, and therefore the coefficient on y is the same, but just with opposite signs, indicating that elimination will be an efficient way to solve this problem. When using elimination, all we need to do is add the two equations together, term by term. Fortunately, this equation already has like terms lined up vertically. The x's are listed first, then the y's, and then the constants, which makes it very easy to see how the addition of our equations will happen. In our example, negative 3x plus 6x is equal to positive 3x. 2y plus negative 2y is the same as 2y minus 2y is equal to 0. The y's cancel each other out. 4 plus negative 10, which is the same as 4 minus 10, is equal to negative 6. The reason we call this method elimination is because one variable, in this case y, gets eliminated when you add your equations. Now we can divide each side by 3 to solve for x. We have x is equal to negative 6 over 3, which is the same as negative 2. Now we can plug in x equals negative 2 into either of the equations to solve for y. I'm going to use the first equation. We have negative 3 times negative 2 plus 2y is equal to 4. This simplifies to 6 plus 2y is equal to 4. Subtracting 6 from both sides, we have 2y is equal to negative 2. Dividing each side by 2, we have y is equal to negative 1. The solution to this system of linear equations is x equals negative 2 and y equals negative 1. Sometimes you have to do a little bit of manipulation of your system to get it into the form for which elimination will work. Consider this system. In order for elimination to work, we need to have the same coefficient on one of our variables with opposite signs, which we don't have here. Sometimes you'll have to multiply one or both equations by a constant in order to get the system into the form that elimination will work with. I could manipulate this system to eliminate either the x's or the y's, but I'm going to focus on the x's in this case. Focusing on the y's would also work, and actually might be slightly easier in this case. Maybe you should try that on your own to see if you can get the same answer as me later. What you need to ask yourself is, what can I multiply each equation by so that I get the same coefficient on x, but with opposite signs? Can you think of what number I should multiply each equation by? Well, if I multiply the first equation by positive 3 and the second equation by negative 7, I think that should work for us. That leaves us with 21x minus 9y equals 30 for the first equation, and negative 21x minus 35y is equal to 14 for the second equation. Notice how we have the same coefficient of 21 on our x term for each equation, just with different signs. Now we can add our equations together to eliminate our x term. 21x plus negative 21x is equal to 0. Negative 9y plus negative 35y is equal to negative 44y, and 30 plus 14 is equal to 44. Dividing by negative 44 on both sides, we get y is equal to negative 1. Plugging in y is equal to negative 1 into the first equation, we have 7x minus 3 times negative 1 is equal to 10. This simplifies to 7x plus 3 is equal to 10. Subtracting 3 from both sides, we have 7x is equal to 7. Dividing by 7 on both sides, we have x is equal to 1. Our solution is x is equal to 1 and y is equal to negative 1. For all the examples we've done so far, there's been a single solution for x and y. There are two other cases you could come across, which I'd like to show you now. Consider this system of equations. This system is set up for elimination. All we have to do is add the two equations together. We get x plus negative x, which is equal to 0, negative 3y plus 3y, which is equal to 0, and 3 plus 3, which is equal to 6. In this case, we have eliminated both of our variables and are left with a false statement. 0 is not equal to 6. That means there is no solution to this system of equations. The lines are actually parallel, meaning that they will never intersect. How about this example? This system is almost set up for elimination, but our y terms don't quite line up. If we subtract y from both sides of the first equation, we will have all of our variables lined up. If we add the two equations together, we get negative 4x plus 4x, which is equal to 0, negative y plus y, also equal to 0, and negative 4 plus 4, 0 again. Again, both of our variables were eliminated, but this time the resulting statement is true. 0 is indeed equal to 0. That means that our two lines are actually the same, meaning there are an infinite number of points of intersection. Our answer is that there are infinitely many solutions, which include any point on the line. Alright my friends, that finishes our video on substitution and elimination.